Okay, it's time, dear students, for me to introduce to you the second real big deal of the semester. The first super big deal was Newton's laws. Kinematics was interesting, right? I mean, projectile motion, you know, the equations of motion, all that stuff. Warmed us up and got us ready for Newton's laws, and that's a centerpiece of the semester. Today is the second centerpiece of the semester, and there's really one following this later on. It's called the work energy theorem. Now, we've talked about work a little bit, a few videos worth of stuff about work. Okay? And what we're going to do today is to take three pieces of information, three pieces of physics, not information really, but three ideas from physics that we've covered so far, and we're going to put them all together, turn the crank, and get this thing called the work energy theorem out of it. Let me show you what the input is going to be for our little our derivation here. This is not an example. This is a derivation of a fundamental physical principle based on everything we've done so far. The first one, okay, and I'm taking these in the order they're going to come in my discussion during this video here, is the definition of work. Okay, and we're going to take the simplest case. Oops. Work is not indicated by an F. We're going to look at this case over here, and we're going to look, before I write these down, I got a little ahead of myself. There's going to be three principles that we've looked at. And we're going to combine these three into a new idea using this scenario right here. Very simple. You got a block on a surface, and you're going to push it to the right through a displacement d, however many meters. The net force is going to be to the right. The net force is going to be, that is, now remember, the net force is the same, it's a different notation. That sigma f, f net, same thing. These three principles are going to have a little different notation maybe than we're used to. That's just to make them all work together. So don't worry about that. You're going to be familiar with all three of these. And so the net force is to the right in the same direction as the displacement. So that means that the net work, or the total work, we're going to use net here, the net work or the total work, the sum of all the works, is going to be equal to F net times D. Okay? And the reason why there's no cosine theta here is because both the displacement D and the force in question, which is the net force, are both in the same direction. So there's no angle between them. The angle is 0. So the net work is simply the net force times D. Okay, I'm applying the simplest equation, the one that we did a few videos ago, when the two are in line with each other. When force and displacement are in the same line with each other, work is simply F times D. So the net work is the net force times D. The second one is Newton's law. Newton's second law, and we're writing it here with the net notation instead of the sigma notation, but it means precisely the same thing. F net is mass times acceleration. Okay. That's just Newton's second law straight up. And it's in one dimension here. We're only dealing with the x dimension, so we don't need to worry about the vector nature of all that stuff. We're along one direction here. Okay, just x. And finally, our third kinematics formula, written with slightly different notation. Vf squared equals V naught, equals, see, look at me, slipping back into the old ways. Slipping back into the old ways, here we go, is Fvi squared plus 2AD. Now, the way we've seen this before, of course, is V squared is V naught squared plus 2 A delta x. Same equation, just slightly different close, slightly different notation. We have the subscript f and I on the v's, and we're using d for displacement instead of delta x. But you'll recognize all three of these as things you're familiar with. And we're going to calculate and combine these three and turn the crank and come out with a new thing. Okay, so let's do that. Let's calculate the total work, or the net work here, done on this block as it moves across the table, starting with initial velocity vi, ending with final velocity v sub f. Okay. And this is probably should be video 7.2a, because I'm pretty certain there's going to be another one from this section. So initial velocity vi, final velocity vf, net work is going to be F net times d. So this is our first equation up there. But F net is ma. Okay, so this was, here, number 1. Now we're going to put in number 2. We're going to substitute ma for F net. Work net equals ma times d, using the second, we've substituted in the second one. Okay. Now what I want to do is to take this one and substitute it in a certain way. Okay. You see this AD here? And see this AD here? I'm going to solve this equation for A times D and stick it in there. Okay? So, what we can do is take this equation, 2AD equals VF squared minus VI squared. All I did there was I subtracted VI squared from both sides, and then I took everything and just flipped it because I wanted AD on the left-hand side. Okay? So 2AD is VF squared minus VI squared, and now I want to divide out 2 on both sides so that it cancels here, and we're left with AD is 1/2 VF squared minus 1/2 VI squared. Okay, now I'm going to take this AD here, this expression here for AD, and I'm going to substitute it there. So now we're going to take the third equation, slightly transformed, and substitute in that AD. So that's supposed to be a 3, but that looks nothing at all like a 3. So let's try the 3 over again. See if I can write this Friday afternoon. So work net now equals M times this thing, right? Because that's equal to AD. 1/2. Jeez. Slipping. I'm slipping, y'all. I'm starting to crack. VF squared minus 1/2 VI squared. So we can write work net equals 1/2 MVF squared minus 1/2 MVI squared. Okay, now you might not understand why we did all this razzmatazz, this algebra. You may not get why we did that, but I hope that you can follow along each step and see that what we did is perfectly legal. So what we end up with is this. Work net is 1/2 MVF squared minus 1/2 MVI squared. Now what I want to do is to look at this and define a new thing known as the kinetic energy K. We're going to define it to be 1/2 mv squared. Okay. Again, no reason why you think we should do this, but we are certainly allowed by the rules of the universe to define this thing. If that's the case, then we can write that work net is K final minus K initial. Okay. Or more compactly still, we can, as we like to do oftentimes, a final value minus an initial value is the change in that value. So we can call this delta K. So what we end up with is work net equals delta K. And I don't have my textbook right here. Your textbook may use KE. I can't remember off the top of my head. It might be delta KE instead of K. I can't recall. If so, I will adopt that next video that I create. But that thing there, okay, I hope you can see how we did this each step. And I don't expect you to see, again, the significance of this or of this. Okay, those are the two big clip and saves here, right? Kinetic energy and the work energy theorem. This is definition of kinetic energy. And this thing here, which is also important, so I'll star it, is known as the work energy theorem. And it is hugely important. And although I derived it here based on this simple case, it is universally true. Okay? It's always dangerous to derive a law from a special case, because maybe it only works for that special case. But I assure you that this rule here, as innocuous and maybe unimportant as it looks to you, is very important and is also universal and applies far more than to this simple situation here. Okay, it's known as the work energy theorem, and it is hugely important. Before I close off the video, we're going to come back to this, believe me, over and over again. Okay, next video we're going to say a lot about it. I want to say one word about kinetic energy. It is energy, okay, and it has the same units as work. It must, right? Work is equal to a change in kinetic energy. If you break down the units, you can see it. The units are joules. Okay, and it is kinetic energy is energy due to motion. We haven't even talked about what energy is fundamentally. But just suffice it to say now that if an object has a mass of whatever it happens to be and a speed, whatever it happens to be, then it has kinetic energy. So I can throw my pen across the room like that. As it moves, it has kinetic energy because it has a mass and it has a speed. So it has kinetic energy. Anything with an M and a V, you can combine it this way and get that object's so-called kinetic energy. But note, just like work, this is hugely important, kinetic energy is a scalar. Even though I threw my pen that way, kinetic energy has no direction to it. Okay, so that pen flying that way has the same kinetic energy as a same pen thrown with the same speed that way. So there's no kinetic energy, no direction about kinetic energy. The pen has the energy, but there's no vector business to it. Okay? Kinetic energy, like all energy and all work, is a scalar. Don't forget it. See you next time when we will do video 7-2B.